Okay, fine. So, okay, so is this screen visible, the graph sheet?
Yes,
Yes, sir.
Okay, fine.
yes, it's visible.
Great. So let's start. So as I was saying, we will start with the discussion on elements of structural dynamics. So whenever we talk of dynamics, any vibration, obviously it's an oscillatory motion. Vibratory motion is an oscillatory system. So there is a interplay. There is obviously a connotation of frequency, number of cycles per second per unit of time, and so on. So the simplest dynamic system that we have all looked at is, I recall my first experiment in the high school physics, simple pendulum. Right? So the way it sustains its motion is by virtue of constant transfer of energy. It is set in motion by initial disturbance. We disturb it from its mean position and take it to one end and release it from that side, release it from that end. So by moving this bob from neutral position to this, we have invested in it some work by raising by this height, and this stores the potential energy in this bob, and when we release it, everything moves from higher potential to lower potential. So this bob starts its journey downwards, and in the process it gains momentum, and entire potential energy gets converted into kinetic energy when it reaches the mean position. So at this point, all of potential energy is converted that was stored here when there was no kinetic energy. The bob was at rest here. So there was no kinetic energy, all energy was in potential energy form. So slowly potential energy starts transforming into kinetic energy, and at this point it is entirely kinetic energy, and by virtue of the momentum gained, it continues its motion on the other side, and then kinetic energy keeps transforming into potential energy until the point it reaches the other extreme position when entire kinetic energy is converted into potential energy, and then it again descends and the motion continues. So now this is very important because in doing so, this pendulum has its natural characteristic. For a given length, the period of oscillation is constant. So that is a natural characteristic of the system. If I change the length, its period will change. Now the time taken to complete one oscillation will change. It really doesn't matter what is the amplitude of motion, as long as I take care that there is no slack in the thread, right? There is no slack in the suspension. So this amplitude of motion really doesn't matter. It is independent of the amplitude. Only the length is the governing parameter, and that is what the physical characteristic means. So the natural characteristic, natural frequency or natural period of system is determined by its physical characteristics. And as we have seen, it is an interplay between the kinetic energy and potential energy. So obviously every vibrating system will have these two basic ingredients. there will be a storehouse for strain energy or potential energy. There will be a storehouse for kinetic energy or the inertia points. And the natural frequency, so we need to have storage for strain energy, or it's the potential energy. And then mass, that is the storage for kinetic energy. So the inertia properties and the natural frequency of the system we can actually derive it mathematically, but let us, that's not really important. Natural frequency of the system in radian per second measure is the square root of this ratio of strain energy storage, the spring constant, and the mass for single degree freedom system. Now, why this is important? I mean, as you can see, it's the ratio of stiffness and mass which defines the natural frequency. And as you can, very well understand, I request you to recall another experiment from high school physics, the resonating column, wherein for different heights of water filled in the tube, tuning forks of different frequencies would actually automatically start vibrating after once we put on top of it, right? So that is the resonance. So we try to find out what is the so that is the resonance, and that has the important implication for engineering design. So if the excitation frequency is close to natural frequency, then the response amplifies dramatically. I mean, there might be several orders of magnitude increase in the response. A typical example is, of course, what I would say, the radio receiver, FM receiver, or even television receiver. How are the different broadcasting stations identified? If you look at it, they are in terms of the frequency, right? So the frequency of broadcast that characterizes each broadcasting station. So as we speak, I mean, as we sit in our houses of safe enclosures, even in that position, we are constantly surrounded by the electromagnetic waves of very small amplitude. But if I tune my FM receiver to the particular frequency of that broadcast station at which it is transmitting its signal at that 102.1 megahertz, then I suddenly start getting very crystal clear and crisp sound from the receiver. That is because the natural frequency of the receiver, when I tune the receiver, I am actually changing the natural frequency of the receiver. So when the natural frequency of the receiver is tuned with the frequency of the broadcast signal, then the response amplifies, and that is what manifests itself in the form of very crisp and clear sound. Otherwise that signal was always there. I mean, we were surrounded by that 102.1 megahertz electromagnetic wave. It's just that our bodies are not tuned to that frequency receiver was not tuned to that frequency, and we did not notice it, right? So that is what happens in case of dynamics. So if I try to present the picture, so this is called tuning ratio, excitation frequency versus natural frequency, and this is what we call as dynamic magnification factor. So dynamic response divided by the static response. What would be the response of the system if it was applied statically, that is at a frequency of 0, the constant force? I mean, the static response is of course when I say force time t is equal, so static response, static force is this. Right? The force has been there constantly applied. There is no constant level. It is held at constant level for all times. So there is no dynamics coming into picture. So that is what we take the ratio against. So this is going to be 1, and you will find that it will something like this, and this happens at the tuning ratio of 1. So when the natural frequency is close to the excitation frequency, then you can see the response that it builds. So the dynamic response is going to be several orders of magnitude larger than the static response. What happens if the force, same amplitude force was applied at a constant, at a constant level, without any oscillation, without any reversal, sign reversals, right? And also the other point that you need to see, that it is dynamic response, it's not only amplifies. So dynamic response need not always only amplify with respect to the static response. It can also go below the static response. If the excitation frequency is very large compared to the natural frequency, then it is also possible that the dynamic response would be even less than the excitation, even less than the static response. So both the things are possible. So and therefore it is important to characterize the dynamic response before we take into consideration for our engineering design, whatever we need to do. And that is why we need compared this with the dynamic force. So this is the dynamic force. Now obviously if I have a simple, let's say, a building system which I can model it as a column, a heavy slab resting on columns, so this can be modeled as M, and this can be column that their lateral stiffness can be referred to as K, and this can be transferred in the form of a mechanical analog. So this is constrained to move in this direction. So lateral vibration under the influence of lateral force. Force is acting in this on the mass, so it is constrained to move only horizontally, and that imposes the demand or the forces on the lateral the columns. And the problem is how to, I mean, this is the critical element. If these columns fail, then the entire structure is gone. So this has to be determined, what is the maximum force that we can expect in the structural system during the vibration, during the application of this dynamic load. What is the maximum force that we expect in the structural system, and we need to design for that. Now this maximum force we can actually identify, there is by application of Newton's second law of motion, we can actually develop the equation of motion. This is the second order differential equation with constant coefficient subjected to external excitation. Now with this equation can be solved, and we can find out what is the maximum response for the given excitation. By solving this differential equation, there are several numerical tools available, time marching tools available for solving this differential equation, but it is not very convenient, as you can see. So I will what is done is, actually if you look at it, I have been telling you about this effect of natural frequency, and I told you about the maximum response. What is the maximum force generated in the supporting structure? Now obviously the maximum force generated in the supporting structure is the force in the spring, if you look at it, right? And the spring constant is constant, it is K, we know this constant. So obviously the maximum force would depend on what is the maximum deformation in the spring. So if I can find what is the maximum deformation in the spring, I know the maximum force in the spring, and my problem is solved. I don't really need to know what is the point to point variation of the force in the spring. As long as I know what is the maximum force, my problem, my basic issue is taken care of, and that's all I need for designing the system. Now this force, if I look at it, so the force in the spring is actually the K times displacement, and this is set off by the in case of earthquake motion, it is the ground motion which is applied. So maximum value is defined by K times U max maximum value over time. So as long as I can find out this value, I can find out what is the maximum force, right? And if you look at it, this U max will depend on natural frequency of the system for a given excitation. Even if the excitation is same, if I change the natural frequency, the maximum response will keep on changing depending on the natural frequency. If the natural frequency is somewhere here, its maximum response is going to be static response multiplied by this factor. If the natural frequency is somewhere here, vis-a-vis the excitation frequency, then the maximum response is going to be determined by this factor, and so on. So it is a function of the natural frequency. So it is important for me to characterize what is the response. If I find out some excitation, dynamic excitation, then it is important for me from engineering point of view to figure out what is the effect of this excitation on systems of different natural frequencies. All systems do not respond uniformly or identically to the same excitation, right? So that brings us to the question of the purpose of strong motion data or use. Strong ground motion data. So the equation that you see, ground motion, let me just take this, draw this picture. So this is the damper that takes care of the energy loss, because any energy transformation, kinetic energy to potential energy, cannot happen without any loss. 100% energy transfer is impossible in case of any physical system. So this is a damper model to represent the loss mechanism. Some amount of energy is transformed into unusable form, heat and loss. So in case of earthquake motion, so the situation is the building or any structure which has the supporting structure and supporting a heavy mass. Now the excitation is not applied to the structure or the mass directly, it is coming because of the motion of the ground. Right? It is the base which is moving, and in the process of this, what happens is there is a inertia. So if obviously the base tries to move in this direction, mass would, because of the property of inertia, it would try to remain in its position, it would resist that motion, and when the sign changes, slowly it will also start moving, but by that time the sign at the bottom has changed, the ground starts to move in the other direction, and then the mass would follow slowly. So there is always a lag between the motion of the ground and the motion of the mass at the top, right? And in the process of that, there are stretch in the spring, stretch or compression in the spring, and that is what causes the disturbance. So if I do this, if I draw the free body diagram of what are the forces acting on the mass m, let me just draw all the forces at any instant of time. So K times U minus Ug. So U is the motion of the mass and Ug is the motion of the support. So net stretch or net compression in the spring is defined by the difference of these two quantities. Similarly, the force in the damper is, we are assuming the simple viscous damping model similar to the kind of suspension systems you have in your shock absorbers of your vehicle. So that is what you have here as the damper. So vehicle shock absorber system is essentially a combination of this kind of spring and damper devices at the simplest level. So these are the forces acting on the mass m, and mass is of course moving by u. So by Newton's second law, we know that sum of all forces acting on the mass m, so this is, we are assuming positive to the right, so sum of all forces acting on the mass m is equal to rate of change of momentum of the mass. Right, so du by dt, that's the velocity of the mass m, and this is the rate of change of momentum of the mass. So I can again work it out like by the chain rule of differentiation. Right. So this is what is happening. Now in case of civil engineering structures, we are fortunate that the mass does not change with time. We are dealing with mass invariant systems. So this term vanishes. Time invariant mass. This is not so in aeronautical systems. Aircrafts and rockets, the fuel is burning at a very fast rate and dm by dt is not zero there. So this term would be present when we are dealing with aeronautical structures. But for the simple civil engineering structures, ground based structures, mass is time invariant and this term vanishes, and we are left with this simple equation, simple term related to acceleration, right? So we are left with let me just say d2. So mass times acceleration, and this is what now this u is the total motion of the mass m measured from a common frame of reference, from the where the base motion is also referred to the same frame of reference. So now if I define, just to rearrange the systems, I define the motion with reference to, let v which is motion of mass with respect to the base. So ug is the motion of the base. So I try to figure out what is the additional motion of the mass. Once I know the motion of the base, what is the additional motion of the mass? So that is what I refer to as Vt, V as a function of t. So obviously this now changes to accordingly k times V minus Cv dot, and this is equal to, now U is now equal to V plus Ug, total motion, so relative motion plus the base motion. So we have m V double dot plus m Ug double dot, and if I transform this equation, then I get mv double dot plus Cv dot plus Kv is equal to minus mug double dot. So that is one way, or I can also write this as m v dot plus ug double dot plus Cv dot plus Kv is equal to 0. Right? So these are the two forms. So essentially this is force in the supporting structure. If I can find out what is the maximum force in this supporting structure, that allows me to design the system properly. What is the maximum force expected in the supporting structure, that the structure that I am trying to design, what is the maximum force that is coming onto it, then I can design the system and I can provide adequate capacities into that. Now this maximum force, obviously for a given K, that will depend on what is the maximum deformation V max, right? Or it will also be equal to whatever the maximum acceleration of the mass, total acceleration of the mass multiplied by the mass itself, because this term is usually very small. Damping term is generally very small. As you might have noticed, in the case of simple pendulum experiment, the pendulum keeps on oscillating for a very long time. So the loss mechanism, there is obviously some amount of loss in every cycle of oscillation, but that loss is very small, and it will take very long time before the entire energy of the system is dissipated away in the form of irrecoverable energy, right? So this damping term is very small. So essentially the balance, if I am looking at the order of magnitude comparison, then it is the acceleration term and this displacement term that actually govern. So either way, if I mean given for a given system, I know what is the stiffness term, what is the spring constant, and what is the mass property. So if I can find out whatever is the maximum deformation in the spring, what is the maximum stretch, or what is maximum compression in the spring, that will allow me to find out what is the maximum force. Or otherwise, if I can figure out what is the maximum acceleration of the mass, then I can find out what is the maximum force, because then it will be equal to essentially equal to the maximum force in the spring quantitatively. they will be balancing each other out, right? From this equation you can see that maximum spring force has to be equal to whatever is the maximum acceleration multiplied by the mass. This term, as I said earlier, this is generally a very small quantity. So the equilibrium is governed by only these two terms. So if I know any one of them, I know what is the magnitude of the force that I am dealing with and that I need to work out. Now as you can see, this is governed by the equation of motion, and this is obviously going to be vulnerable, sensitive to the natural frequencies of the oscillator, as we discussed here in this case. So whatever is the natural frequency of the oscillator, its response is going to be different, dynamic response is going to be different, and therefore what we need, what we typically use is response spectrum. So typically what we do is, there is a ground motion, let's say this is the ground motion UG double dot T, and there are different oscillators. Let us say oscillator with the period T1, then there is a different spring mass system with natural period T2 or omega 1, omega 2, T3, and so on. So different oscillators. The point is, all these systems, they are excited by the same ground motion. So obviously their response are going to be different. So this one we will have let's say V1T will look like something like this. Okay, not really very good representation. And V2, as you can see, this is a very short structure, so its natural period is going to be very small, kind of stiff structure, I mean pendulum with shorter length. T2 is slightly longer than T1, so its natural frequency is going to be slightly somewhat larger, so it will have a relatively long period motion, filtration. Then T3 or V3, the response of the third system is obviously going to be kind of like this. So this is what is T1, max over time t. This is the value V2 max over time t, and this is of course V3 max over time t. So what is done is we plot, this is the maximum response. So if I want to find out what is the maximum force in this supporting structure, I just need, I know the stiffness of this system, K value for this system, stiffness of the spring constant for this system. So if I know what is the maximum deformation in this system due to this earthquake, I will just multiply, I can just multiply this with stiffness or the spring constant, and I get the maximum force in the spring, and that is what I need. So typically this is what is done. Alternatively, I can find out what is the total acceleration, and I multiply with the mass and I get the force. So T1, T2, T3. So some value and I draw this curve. So this is what we call as spectral displacement. Or I would just say relative displacement spectrum. So the importance of this, is whenever we have this ground acceleration, now coming to this strong motion data processing part, if I have this ground motion data, ground acceleration data, I analyze, I integrate this equation of motion for this ground motion data and compute this response for different natural periods. So this motion, actually, if you look at it, the equation of motion that we discussed that earlier is this, and I can by dividing all through by mass m, this can be converted into right. So this equation of motion can be solved for given value of natural frequency. So T1 would omega n is of course equal to 2 pi over Tn. So for different values of oscillator natural frequency and for a given value of damping ratio, we can find out what is the maximum, what is the response like this. So for omega 1 we computed this time history, for omega 2 we computed this time history, for omega 3 we can compute this time history, and we extract the maximum response. Now as I told you earlier that this term is very small. So essentially what we are dealing with here is omega n square V is approximately equal to if I take the absolute value. right? So this gives you maximum response, maximum amplification. So this gives you the acceleration spectra. Again T1, T2, T3 spectral acceleration. So you will have some value something like this. Right? So what you are commonly referring to as the peak ground acceleration, that is the most commonly used referred to parameter in seismology, strong motion seismology. Peak ground acceleration refers to just one point here. Peak ground acceleration is when V double dot is 0 and we are only looking at maximum value of this ground acceleration. So this V double dot is going to be 0 when there is absolutely no deformation of this in this supporting structure. It doesn't move, it doesn't budge even by any small amount. That can only happen when it is an infinitely rigid system. So that for that system there is no oscillation possible, and that is referred to as zero natural period. Its natural period is 0 or its natural frequency is infinite. There is the stiffness is very, very high. It's infinitely rigid system. So the peak ground acceleration refers to this zero period acceleration when the natural period of the system is 0. So this is what it refers to as the peak ground acceleration. And that has only a very limited applicability. Most of the dynamic, it doesn't capture the dynamics of the vibrating system, and therefore peak ground acceleration on its own has very, very limited application in engineering design. So we are looking at these are the two alternate representations, relative displacement spectrum or absolute acceleration spectrum. As you can find out, as you can figure from this, absolute acceleration is approximately equal to, if I can find out relative displacement and multiply it by square of the natural frequency, it is approximately equal, and that gives us, this is what we call as pseudo spectral acceleration. Because if you look at it, the units, discard the radian measure. So this V has length units, and then there are t square units in the denominator per second square. So this has the units of acceleration. So this is what we call as pseudo acceleration. So if I compute what is the maximum relative displacement, multiply by omega n square, I will get something that is very close to the absolute acceleration, but I call it pseudo spectral acceleration. It will be exactly identical. The approximation changes to equality if I am dealing with undamped system. If zeta is 0, then of course this equality holds rigorously. So pseudo acceleration is equal to absolute acceleration in case of zero damping, but when the damping is very small, then it is approximately equal, and one acceleration, pseudo acceleration, can be derived from the displacement spectrum and vice versa. and either of these forms can be used to estimate what is the maximum force that is coming onto the structure because of earthquake and which we need to design for. And that is what is a crucial aspect of understanding the requirement from a strong motion data. Why, how do we use strong motion data, and in what form it is to be used, and how it is to be archived for meaningful use for engineering applications. So I'll stop at this point. If you have any question, please feel free. Hello?
Manish sir,
Uh-huh.
sir, one thing.
Yeah.
When we talk about strong motion, does it mean very small earthquake, say of magnitude 4,
Uh-huh.
near to my structure? Is
Uh,
it strong motion, sir?
देखिए, strong motion, that terminology comes from the instrumentation side, right? क्योंकि आपके जो seismological instruments हैं, seismometers typically, they are very very sensitive instruments. I mean, you can record earthquake occurring in Chile. You can record it in your network, your instruments which are installed across all your dam locations here, right? So they can detect very small, very imperceptible motion जो हमें पता नहीं चलते हैं. That's how we record the smaller earthquakes, magnitude 2, magnitude 3 earthquakes भी record होते रहते हैं, right? So those are weak motion. And as I said earlier, the weak motion, small earthquake motion, they have different frequency composition. आपका corner frequency model है, omega square model है. So as the magnitude increases, the slip increases. I mean, there are more slip happening in the fault, and more long period waves are generated. More energy is released in smaller frequencies. So the frequency spectrum shifts towards the smaller frequency. So that is one thing, that is frequency characterization. But there is also an aspect of amplitude itself, intensity of the shaking. So your seismological instruments, mostly seismometers, they would pick up very very tiny, very very minute amplitudes of ground motion as well. But when a strong earthquake or a very strong intensity motion happens in that recording site, the instrument, because it is very sensitive, obviously its range is limited. These instruments would go off scale. You will see the clipping happening. If you have a installation of seismological instrument, seismometer and strong motion accelegraph at the same station, you might look at the data and you will notice that there is a clipping beyond the limit of the seismometer. And that is why we have this strong motion terminology. The strong motion instruments, they are very robust instruments, but they cannot, obviously they are designed to record such very strong intensity of motion, and obviously their sensitivity is very small, is not as sensitive as the seismometers. So these strong motion instruments, accelerographs, they would generally not record very small vibrations. Distant earthquakes or very small earthquake, they would just not trigger, they would just not record anything. So that is the context of strong motion instruments, strong motion data. So was I lucid enough to?
Yes, sir.
Okay, fine. So, any other question? Okay. So, I guess all of you have that document, the paper that I shared earlier, Boer and Bomber.
Yes, sir, we have got that.
Yeah, sure. So, from our next week, we will go back with this introductory background about how we use the strong motion data in engineering analysis. Now you can probably appreciate it better that it is not just the acceleration trace that is important. Peak ground acceleration is just one point in that entire spectrum of maximum response of different oscillators of different natural frequency, and that depends on the physical characteristics of the structure that we are going to design. Typically, concrete gravity dams, natural frequency, natural period is in the range of 0.2 second or so. So that actually happens in the maximum amplification range of the response spectrum, as you can see. So, but in general, for earthquake resistant design, you need to look at the natural frequency of the structure, and that is how you ascertain how it is, what kind of information would be relevant for the structure that we are designing. And accordingly, we need to provide the information, we need to distill this information from the waveform. Not everybody is capable, or not everybody has the background to interpret the waveforms correctly or to retrieve the required information from this waveform. So it is our job to distill that information and provide this information in the usable form to the users, that they can understand and they can use it correctly, right? So that is the purpose that we will have at the end of this course. We hope that we should be able to define a standard operating procedure of processing the strong motion data and then archiving it, and then using it for our future engineering design operations. So from next week onwards, we will go back to our strong motion data processing, starting with the acceleration trace as we record, and then what needs to be done before we can use that acceleration trace for further analysis. Okay. So if there are no more questions, I will stop. With your permission, I will stop the recording. Kapil sir,
Excuse me, sir.
yeah, please.
Sir, as you said that we will be starting in next session with the acceleration records. So can we then have some our own records also, which we can use for this? Can we keep some records ready?
We will do that hands-on data processing after we cover some ground. I mean, what theoretical ground. So next lecture will also be more of going through the basic issues, and then we will from maybe from the second week we will start working on the data.
Okay, sir. Okay, sir.
Right?
Thank you.
Yeah.
Yes, I think जो आज का जो लेक्चर था ये काफ़ी अच्छा था, इंटरेस्टिंग था, और मेरे ख्याल से काफ़ी लोगों को हमारे यहाँ जो है ना क्लैरिटी डेवलप हुई है इसमें कि वाई वी आर यूजिंग दिस ग्राउंड मोशन, एंड वी आर फॉर्चुनेट दैट वी आर एबल टू लिसन टू यू एंड अदर पीपल आर आल्सो गेटिंग दिस अपॉर्चुनिटी. So any other question if anybody has?